And here we are once again. Welcome back to the ARC Agency's formal CPD day and our 5th session of the day. Thank you again for joining us. My name is Brooke, and on behalf of everyone involved today, I would like to thank you all for attending. Let me outline our steps for success. You must be registered for each session you wish to attend. Please check the chat for invite details should you wish to add any extras. Each session will run for 1 hour and the sessions will start on time with access closing 5 minutes after its commencement. CPD certificates will be issued by the presenters and recordings of the sessions are available upon request. We encourage you to ask questions via the Q&A function, which you will find at the bottom of your screen in the black control ribbon. As part of the formal assessment and guidelines, each presentation includes a questionnaire which you are required to complete and is to be kept for your own records. Please ensure, if you have not done so already, to download the appropriate questionnaires for the presentations you are attending. I have just updated the chat function to include this link for easy access. I would like to thank you all for joining us, and in our 5th session, Laros Group Director Michael Kingsland presenting Condensation and Healthy High Performance Homes. Thanks, Michael.
Good afternoon and welcome to my presentation about condensation and how to get to healthy and high performance homes. This is really structured as an introduction to building physics and solutions to the most common problems in construction, which is really condensation and condensation causing mold. One of the biggest issues I think that we're facing in Australia with the building industry as it is. And just a bit of background to our business and myself. So Laros Technologies started in 2009, purely with solar technologies, so photovoltaic, and transitioned to high performance buildings from 2012 onwards. The CEO then used to be the former director of the Swiss Institute for Testing of High Performance Building Technologies, so he was really on the forefront of that development and knew all the kind of really the cutting edge technologies, and we started bringing them in to Australia. It was one of our passions, and really from the very beginning our approach was based on building physics, and you might have heard about the passive house standard. So we're using passive house standard principles, as the passive house standard really is the only building standard in the world, as far as I know, using truly holistic building physics approach. My own background, as you can hear from my accent, I have a German background. I have a German physics diploma, which is roughly equivalent to a master's in physics in the English system. And after arriving in Australia in 2004, I didn't quite know what to do, so I went back to uni and did a master's in engineering as well. And then later in 2012, I joined Laros Technologies, at the time just in the transition towards high performance buildings. And we grew that part and finally stopped doing any solar technologies. In the end, in 2018, the business was split. So one of our product lines from Germany always said, like, if they think things are going well, they want to set up their own daughter company, not sell through us. And they basically asked our CEO if he wanted to run it for them. And he said yes. So in 2018, we split the business into the new daughter company, Ryco Pacific, and a new Laros Technologies Australia, led by me. In 2019, then we wanted to develop things a bit further as well. And looking around, we weren't quite happy with current standard building techniques. Prefabricated building is really growing very fast, and we did a few prefabricated collaborations and found there were some issues. So we started developing our own prefabricated building system with a new business called Laros Structures. So we started the Laros Group in 2019, Laros Structures doing the prefabricated building system, still Laros Technologies providing all the products, and also started a new branch in Laros Consulting, where we then offer consulting services to people with around building physics. For example, we offer thermal bridge analysis, hygrothermal modeling, and the passive house modeling as well, the PHPP analysis. The learning outcomes we want to cover in this talk are condensation. Again, condensation especially causing mold, which is eventually what happens if you have lots of condensation in your building. When and how does it have a building condensation and moisture issues, and how can we avoid them? We cover also the modeling for those building physics conditions. We're using, as I said before, thermal bridge analysis and hygrothermal modeling or WUFI modeling. To battle condensation and mold, the easiest and most effective thing is to increase air tightness in the building. So I want to cover air tightness and how it does affect moisture airflow and also the thermal performance of the building itself, not just moisture. You can design for an airtight building, but in the end, once it's built, the only way to figure out if it's as it was designed is to test what happened during the construction. There's a so-called blower door test, and that should really be the quality insurance for every single building project. And we're working towards it. It has been considered by some government bodies as well to look into pilot projects to see what the building industry is at. CSIRO itself earlier did a test of the status quo in the building industry, measuring the air tightness of many buildings, and found out they're very leaky, coming to at roughly 15 to 20 air changes per hour at an equivalent of the pressure difference, and that would be at a 30 km/h wind, which is 50 pascals. To help with air tightness design, there are some tools. The easiest and most simple one is a piece of paper and the so-called red pen test. So use a red pen, you run it around your building envelope and figure out where the air tightness envelope actually has to be, because not all parts of the building have to be included. So that's a very useful tool, very simple. That red pen test can also be used for other things that I'll cover later with the structural thermal breaks. If you have an airtight building, there's no way around ventilation strategies. So people don't want to suffocate, and to keep a good air quality inside, somehow the building needs to be ventilated. So I'll cover that, and in the end, I will cover structural thermal breaks. Again, having an impact on condensation and mold in the building. And structural thermal breaks are unfortunately often still overlooked and put into the too hard basket. It's actually not very difficult. Technologies have been around for more than 40 years now in Europe, and pretty much everything that should be thermally broken, thermal bridges, they can be done. So I'll cover that as well. At the moment, we're facing a very big drive towards higher energy efficiency for obvious reasons. We're facing climate change. We have to try to reduce energy consumption, and energy efficiency in buildings plays a big role in there. But often energy efficiency battles a bit with value engineering. We require buildings to do certain things to be more energy efficient. There's new technologies coming in. People are not quite sure how they're done, or they're very expensive. So there's a very strong push against those things. Often certain parts that should be done are value engineered out. And to reach energy efficiency goals in the end, it's a bit of a numbers game. So some things are cranked up, others are kind of disregarded, and that causes problems. So what happens really is a very imbalanced approach to construction. A bit like the person here. So we increase one part, we make the upper body nice and warm with a nice down jacket, but the pants are forgotten, and overall the person is warmer than with thin pants and a t-shirt. So another thing, another example or equivalent kind of that I like to make is like you have a fancy car, you build a very nice home, it looks really good on paper, but some things are still left out. So it's a very high quality product, but it's not very comfortable to sit in or drive in because the wheels are missing, for example. And another really nice example that I like is the doona with holes in it. If people again have a doona that has holes in it, you can increase the energy efficiency of the building by just increasing the thickness of the doona. In the end, what happens? The building uses less energy, but is it comfortable? Does it really work for the inhabitants if you have holes in your doona? I don't think so. So what the result from this is in the end is we have undesirable side effects. we create unhealthy buildings by forgetting some bits. We're actually causing condensation and mold growth in buildings. If we would turn the whole thing around, instead of looking as a primary goal as just energy efficiency, have instead healthy and comfortable buildings, we would actually get automatically more energy efficiency and efficient buildings as a desirable side effect. But what's needed for this is a balanced approach. We can't just increase one side and forget about other things. You have to move all those sliders in the same fashion, in the same way. And it doesn't always have to be a passive house, for example. But if you have a balanced approach, you can easily avoid problems like condensation and mold. One other thing that I think causes problems with condensation and mold is that how our understanding of how moisture transport in a structure or in a building works is not very intuitive. And for this is really important to understand what relative humidity actually means. Relative humidity is our description at a certain given temperature, how much water air can hold, basically. So, you know, everyone, I believe, knows at a certain temperature, there's a maximum amount of water that air can hold. If you go above that threshold, you get condensation, but you don't actually increase the amount of gas, of moisture, vapor inside the air. You just increase the, what happens in condensation is that you happen to have water droplets. First, you create mist or fog, and if they get bigger, then in the end it rains down. But the actual amount of gas in the air doesn't increase above 100%. This is the same for 0 degrees or 20 degrees, but the amount of gas that's in the air at those relative humidities is quite different. So you can see on the right-hand side at 20 degrees, we have way more moisture vapor in air compared to 0 degrees. So what happens then at the same relative humidity, we have a drive from higher humidity, higher moisture vapor amount to a lower moisture vapor amount. And I think if we take this approach, and the thing that actually drives the moisture transport through your building from the inside to the outside is a pressure difference. And you can relate the pressure difference or the pressure of water in air with the amount that you have compared to the amount of all the other gases. So those little dots now stylized little kind of water droplets in that volume, for example, represents the amount of vapor gas in the air, and the blue is just making up all the other gases. At ambient pressure, the total is always, no matter what temperature it is, roughly 1 bar. But at 50% relative humidity at 20 degrees, we have a certain amount of moisture, and that partial kind of amount, so it's almost 1/100th. So 1 bar is roughly 100 kilopascals. In the end, we have only 1 kilopascal of water vapor. At 0 degrees, this looks quite different. So we have a lot less moisture, and with that also a lot less pressure. And because the amount compared to all the other gases of water vapor in air is a lot less. And this lower pressure relates from inside to the outside than if we have warm inside, cold outside, to a pressure difference. And this pressure difference means we have a pressure of 600 pascals, or roughly 600 pascals, trying to drive moisture from the inside to the outside. And this happens even at very low relative humidities. We have still more moisture on the inside at low relative humidities at higher temperatures compared to outside. So we still have a drive from the inside to the outside because we have a higher pressure on the inside. So I think really if you throw away relative humidity and get rid of this kind of intuitive understanding of how we relate to moisture in our environment and look at moisture pressure, vapor pressures in air, or the pressure of water gas in air, then it makes a bit more sense. And we understand that no matter what conditions, almost always moisture travels from warmer temperatures to colder temperatures. And if we have our winter condition here again from the previous picture, that's exactly what happens. We have moisture driving from inside to outside, disregarding what relative humidity we have. In the end, with the building structure, what happens is, if we, for example, take now the standard construction, gyprock, insulation, and brick veneer, for example, gyprock is not perfectly moisture tight. It's airtight, air can't travel through, but it's slightly permeable to moisture. And this big pressure difference that I described before from the inside actually pushes moisture through the gyprock towards the outside, through the insulation. On the way towards the outside, it gets colder and colder. Eventually, it starts to get to a point where there's too much moisture in the air. You exceed 100% relative humidity, so you get condensation. And the amount that we can actually drive through gyprock, where we think we have a fairly good airtight seal on the inside, still we have moisture traveling through over a 90-day period with those conditions of 20 inside and 0 degrees outside, amounts to 6 kilos or almost 6 liters of moisture per 1 square meter wall. So it's a massive amount. It's a small bucket of water basically just tipped into your wall cavity, sitting there in your insulation, causing the insulation to be wet. Energy efficiency drive now doesn't really account for that in our understanding of the building system, and our National Construction Code doesn't really allow for those kind of things, or hasn't for a long time, slowly changing. So what happens really with the drive to more energy efficiency, the only thing that we're looking at is to increase the amount of insulation. But in the end, it doesn't change the fact that we have large quantities of water traveling from the inside to the outside, making our insulation wet. And everyone knows, I think, that wet insulation is a much better conductor than dry insulation. So what looks like we have an R4 or R3.5 insulation on our walls, in the end ends up wet insulation, and performing way worse than what we think we have. The second type of moisture flow through a building structure, rather than through the gyprock itself, can be air leakage driven moisture flow. So if we look, for example, at bad construction, there's gaps, for example, around windows, or connections from walls to ceilings, not really tightly done. There are actual holes in your wall, and of course, air can go through. This air carries way more moisture with it already than it could go through the gyprock itself. So that moisture transports a lot faster. So we think, okay, that's a problem with bad construction, so we easily fix it. We just make it better and close all those gaps. But there's many gaps that we can't actually close, or not easily close. For example, power points. Those things look tiny, but if you're actually on a slightly windy day, hold your hand in front of your power points, you can actually feel air coming out of your power points. You can feel that air pressure coming through there. Another, or almost the worst thing in a building is cavity sliders. There are massive openings behind that are usually not sealed. Air can travel straight through from the warm inside environment into your wall spaces, into your cold roof structure, or into your external walls, taking all that moisture that's in internal air towards the outside, again creating condensation and mold. This has been tried to quantify or get a bit of a better grip on it to see how bad the effect actually is. And so in Stuttgart, and people did in Germany, people created an experiment with a 1 square meter gyprock wall, insulation of an R value of 3.3. And then they cut a 1 millimeter gap into it, and created inside conditions of 20 degrees, outside conditions of -10 in a test chamber at a 20 Pascal pressure difference. So they had a fan kind of blowing wind through that gap as well. 20 Pascals is roughly equivalent to 20 km/h wind. So 20 km/h wind, again, not very strong, but it's certainly noticeable, and good breeze. And they found, I think I went a bit too far here, and they found that the performance of the insulation went down from 3.3 to 0.7. So that's a factor of almost 5 down from what people expect to have in their walls. I think I skipped over the previous slide. I'll just go back a bit and noticed it all popped up at once. So the same experiment was done also just to determine the amount of water running through that same gap at the same conditions. And after a 24-hour period without any gap cut into the gyprock and just moisture going through the gyprock itself and diffusing through, they found 0.5 gram of water after 24 hours. And after cutting that 1 millimeter gap, they found a 1600-fold increase, so almost 1 liter of water just in one day being dumped into the insulation through that 1 millimeter gap, just by having a leak in your building. So you can see that that really is massive. So building well on the inside. And again, the same, just even if you don't take moisture transport into account, looking at the thermal performance of the insulation itself, building well on the inside makes a big difference. And air tightness is, of course, the solution. So if we increase the air tightness of our building, we can make the thermal performance of our building better, but we can also reduce moisture transport through our walls, or perhaps completely eliminate it with the right technologies. If we look at the reverse though, so if we now assume we have a well-built building and we have a high air tightness on the inside, what happens if there's some gaps from the outside in our external kind of building envelope and a bit of wind? And this was really triggered by just a normal thermal camera test, and people in Poland went to an apartment under an attic to try to determine the thermal performance, and they found this really intense cold spot. And the first conclusion obviously was, okay, there's a corner here, they insulated that wall, but they kind of missed the corner and didn't really wrap around. And what they did in the end, they had to look into the structure from the outside, and they saw there's no kind of gap in the insulation at all. It's perfectly well insulated. So what was happening? They did an air leakage test to see if maybe there's a gap or something, but they found the air tightness test was very good. Only 3 air changes per hour. I said before, Australian kind of standard construction is somewhere between 15 and 20 at 50 pascals. So that's actually a very good result. Then they had a bit of a closer look at the construction itself. So what was happening? Again, as I said, on the inside, they had a fairly airtight envelope, good gyprock construction, insulation, and the roof. And on that roof, under the roof, they had a wind barrier. They had a building membrane sarking, basically. What they found, though, that the joints of that external wind barrier were not taped. So it was just simply overlapped, basically as a weather barrier, keeping the rain off if there was any kind of leak through the roof or something, but not really taking care to tape it and keep the wind out. Again, they tried to quantify the effect that wind has on insulation in walls, and they created 2 models, one just with gyprock and R4 insulation and no wind barrier at all on the outside, and one the same, but then they added a leaky wind barrier, the same as before. They had insulation sarking on the outside. They overlapped it, but they didn't tape the gaps to test what happens and what the effect is of different airflows over the insulation. So basically the wind wash over the insulation. They applied a number of different wind speeds. Again, meters per second might not be intuitive for everyone. If you take it as equivalent, so 100 kilometers per hour is roughly 26 meters per second. So roughly half a meter per second is a very gentle breeze. You can almost not feel that. So they applied those 4 different wind speeds and check what happens. And even at that very low gentle breeze that you almost cannot feel wind wash over the insulation, it had such a big effect on the insulated value, insulated performance of that structure, that the performance dropped by almost half. At higher wind speeds, the effect was even more significant. So they had 2 kind of measuring areas on the other side of the wall to measure the thermal flow through the wall. And on one point, the thermal performance actually dropped by almost 90%. So you think you have R4 walls, you don't have a good wind protection on the outside, bit of wind wash, and you only have R.4. So really nothing. The same happened with the leaky wind barrier, not quite as bad, but the effect was still significant. So 2 different measuring areas, again, one very close to the gap, to the overlap in the wind barrier, one a bit further away where the effect wasn't quite as bad, but still you got half the performance of R4 that you should have expected at the highest wind speed, and close to where the gap is even less, so 70 to 80% reduction of thermal performance. So air tightness, not only from the inside is important, but also looking on the outside of the building has a very big impact on how your insulation actually performs. So we covered at the moment moisture and reduction of performance of the insulation by moisture. Wet insulation performs worse than dry insulation, but also dry insulation that has a bit of wind wash over it makes a big difference. The R value reduction can go up to 90%. Again, we try to address all those problems. Now we have a continuous taped air barrier on the outside and a continuous air and moisture barrier on the inside, trying to stop moisture going through. That's the optimal construction that you can have, really, to stop moisture transport into your wall, but to stop also wind and air leakage through all those things. And the best way to do that is with an internal membrane protecting the insulation, and an external membrane keeping wind and weather out. Standard construction, again, here though, is still to have a structure, for example, a truss roof, where basically ceiling beds are just put on top of the ceiling. Again, there were studies done, and insulation really works well by trapping air. If the insulation can't trap air well, then it doesn't really work as well as you think it should. If someone has ever held a piece of insulation bat, glass wool, for example, in the hand, and you, for example, try to blow through it, you can feel virtually no resistance. So insulation bats, for example, on their own, are not a very good medium to properly trap air. What we have then, especially if we have very warm conditions on the inside and cold conditions on the outside under the roof, everyone knows warm air rises. This warm air close to the inside is more buoyant than the external air. And what actually happens is we can have convection current starting to happen. Despite being completely airtight on the inside, completely windtight on the outside, warm air rises and sinks down again. And this circulation actually reduces the thermal performance of the insulation. At the university in Finland, they tested this as well. They created an experiment with a truss roof and in a heat flux chamber, did different insulation levels, and they found that the heat flux through the internal convection, just by having insulation sitting without the cover on top, so having a big airspace above that air can move freely through, the performance of the insulation went down by 68%, or the heat flux through the insulation went up by 68% compared to the value that you would expect to have. Again, if we look at the R4, this would be less than R2, simply by sitting in your roof, despite being completely airtight on the inside, completely airtight on the outside. So in terms of airtight design, one can't only look at protecting from the inside, protecting on the outside, but also minimize really the space the insulation has for air to move through. So you need to trap the air within the insulation and don't allow it to escape. And the easiest way in this case would be to just put some cover, some kind of cover on top of the insulation. It's not even that important, because the airflow through convection is so gentle and slow. You would not necessarily have to tape the joints. In this case, there's no actual wind driving through. But we had a client who did this as well, and as you can see, the result is very spectacular. So insulation on top of your ceiling, completely covered with a membrane, completely stopping the convection going through. And in the end, the R4 or R5 that person had in their roof could finally now actually also perform as an R4 or an R5, and not what people think. They actually have. Another easy way, or the best way really, to avoid kind of those issues with truss construction and having to do extra steps to protect that insulation again, would just simply to build a sandwich roof panel. This allows you for optimal trapping of air. It also helps to increase the usable space inside your building, so it allows for a usable attic. And for example, if one starts looking at prefabricated construction, it allows for a much easier panelization of that building structure. So again, looking at the importance of airtightness, there's a whole range of solutions and systems that can help. So I briefly covered an internal membrane to stop air and moisture leakage from the inside. There's an external membrane to protect from weather and wind, from rain and wind. All the little penetrations like power points and cavity sliders and everything, and electrical penetrations, plumbing penetrations, there are solutions for this to seal everything perfectly. So you can actually create the perfect sealed envelope without convection around it, and without wind driving through, without moisture going in, and in the end end up with a healthy building. This is fairly easily done, actually, if one thinks about it during the early design phase. If it's done as an afterthought, it becomes very difficult to retrofit and very expensive very quickly, because the labor that's involved becomes very tricky and finicky and very complicated. Again, to help with the early design to consider air tightness, there's the so-called red pen test. A very easy kind of tool. As I mentioned before, not every part of the building needs to be considered, and to actually figure out where all those airtight barriers and weather barriers have to go along, use a red test for your building. And if you're in your design phase, you might actually end up at some tricky junctions that you now still have some chance, maybe by design, by changing little kind of things, moving the wall from here to here, for example, just make the whole junction later through this through construction easier to seal. And the red pen test again helps to visualize all those kind of tricky points. You see where you have to cross through to make it airtight and weathertight. So that's a fantastic tool for architects to very early address that issue and to design better and healthier buildings. And at the end, that red pen kind of drawing can even be passed on to builder to act as a guideline when they then have to actually implement the airtightness measures to see where exactly they have to put them along. And in the end, also that whole thing can be used for verification, as I mentioned before. If you want to build airtight, it's not enough to just design for it. Builders do all sorts of things on construction sites. They try to do their best, but if you give them a target, if you want to achieve a certain performance, if you want to make sure that you can avoid condensation and mold in your building, you have to verify it. And the only way to make sure that it's properly done is with a so-called blow door test. In this case, a so-called blow door, so which is a frame that seals in an opening in the building, is installed in a doorway, for example. There's a big fan in there that's calibrated and sucking air out of the building. The pressure difference between inside and outside is measured. You drive it up to 50 pascals and measure the amount of air that flows through. And the amount of air that flows through the fan has, of course, at the same time, has to be the air that leaks through gaps and cracks. When you run this test, you can actually go around the building then and find leaks. It's a very good tool. You can either have a little kind of smoke generator or smoke generators are the easiest to go around the building, see where air leaks through, and easily rectify those problems, and again get a better outcome after the building is finished. Again, making sure that there's no condensation and mold inside your structure to make the performance to make the insulation perform as it should, and give the building give your clients what they actually expect and what they paid for. In terms of construction, building, and design. If you now have an airtight building, it's pretty obvious you need to somehow ventilate it. Natural ventilation is, of course, still possible. People still want windows in their buildings. Often people think, oh, high-performance buildings, I need to avoid condensation and mold issues. I can't really open my building anymore. I can't open windows because it has to be airtight. Of course, you could ventilate by opening doors and windows, and that can still be done. So natural ventilation is still possible. You just don't want this uncontrolled natural ventilation just through gaps and cracks, because it can cause the problems. The problem with so-called controlled natural ventilation through doors and windows is you actually rely on people to do it properly. And the problem is, yep, you can ventilate naturally, but can people be really relied upon to always do the right thing? If it's 0 degrees outside, are people going to open their windows to let fresh air in, or the doors? If it's 40 degrees outside, the same thing? Usually not. And again, another result from this is like, yep, natural ventilation can be done, but a better way is to use mechanical ventilation that takes the person out of the equation. Also with this, you can automate things, of course. Smart homes become more and more important, and building control. And yeah, mechanical ventilation is really the best and easiest way to do this. So the best solution overall is heat recovery ventilation or energy recovery ventilation. I'm going into the differences a bit in a second. The great thing about heat and energy recovery ventilation as a balanced ventilation system is it always keeps the inside conditions as they are. So it keeps the hot side hot, the cold side cold. So in summer, for example, if it's hot outside, the warm air that comes in is conditioned by the outgoing colder air. It's cooled down. it almost comes in at very efficient heat recovery at the same temperature as the air that left. So it keeps the conditions cold inside and keeps the heat outside. In winter, the reverse, the warm air on the inside warms up the incoming cold air just through a passive heat exchanger without needing any active heating or cooling at all in this case. And again, the nice and warm, comfy conditions inside are maintained just by simply blowing air through a heat exchanger. Those energy recovery ventilation systems can be very, very efficient, so up to or even slightly in excess of 90%, which then massively also reduces heating or cooling loads that other mechanical systems might have. In Australia, in a high performance building, you can build in a way that you won't ever need heating and cooling. And passive houses have been built up in the Swiss Alps, for example, at 3,000 meters, building that simply rely on the people that live in there, body heat generated for cooking and having a few showers. And there's no other active heating system. That's at the permafrost, 3,000 meters up next to a glacier, basically, in the Swiss Alps. The other case in terms of cooling is not that easy, especially with climate change progressing. We are now facing more and more hotter summers. We have conditions on the outside over many weeks where maybe the temperature on the outside doesn't go really much below 20 degrees. So even if we bypass in that case, when we get cooler conditions outside and inside, the heat exchanger and bring directly the cooler air in, it's not cool enough to really stop that slow creep up of heat gain on the inside. So we still require a bit of air conditioning to cool down in summer. But it's again with a high energy efficient building envelope, a very airtight envelope, and the energy recovery ventilation system. The load that we need is significantly reduced to standard construction. On the other hand, also having a very airtight building envelope and having constantly filtered air coming in 24/7 gives us a very good indoor air quality, no matter what happens outside. Very good for people who suffer from allergies, for example. If there's pollen outside, they get filtered out of the air. Even bushfire smoke, there are filters that are fine enough to filter up to 70–80% of most of the PM2 micron particles in smoke, giving you very, very good air quality on the inside, better than having a leaky building and trying to use an air purifier. And at the same time, with that ventilation system, we have an improved moisture and humidity control. We don't have to rely again on opening doors and windows. We still create moisture on the inside through showers and cooking and just evaporating through our skin, but the ventilation system takes care of that. Now there's two general kind of types of ventilation, either centralized ventilation or decentralized. Each of them have their kind of economic sweet spots and their best use cases. For a very small apartment, for example, you don't really need a centralized system with lots of ducting going everywhere because there's nowhere to go. In that case, you can do a small system that just simply punches a hole in the hole into the wall on two sides of the room, for example, and one pushing air in, the other one pushing air out with a heat exchanger in each. And they work in a way that they change the direction, for example, just before the heat exchanger is fully charged with, for example, in winter, cold air coming in and warm air going out. So the warm air going out heats up the heat exchanger just before it's fully hot, and the system turns around, and the cold air then coming in through that warm heat exchanger gets warmed up. And those systems are very efficient, as I said, around 90%. For bigger, more complex buildings, overall, you will be looking at a higher cost using those decentralized systems. So it becomes more effective than to run a bit of ducting and one centralized unit. The other advantage also with this is that you can actually equalize your conditions throughout your building in terms of temperature. So if you through one part of the house have lots of sun coming in, for example, and the air conditioner, you have an air conditioner split system in another room, the ventilation system can extract from that cooler room, run that cold air through the heat exchanger, and inject then the cooled down external air into the warmer room and cool it down. So over time, the overall temperature conditions in the building equalize. That also allows you to install a smaller and simpler air conditioning system, as I mentioned before. So we'll still need some air conditioning, but you can tuck it in away in a back room, for example, where you can't see it, you can't feel it, you can't hear it, and it still helps cooling down your house. Then again, there's two general types of technologies that can be present in both centralized and decentralized. You might have heard of energy recovery ventilation versus heat recovery ventilation. Energy recovery ventilation usually recovers moisture as well. So there, for example, in this case, there's a rotating wheel heat exchanger. You have two separate air streams that are separated by a membrane or by a metal sheet in this case, for example, but there's a little gap, and there's again seals towards that rotating wheel. The wheel is a structure like a honeycomb. It's got lots of little pores. The warm airstream from the inside, for example, in winter, moves through this wheel. The wheel rotates and takes the warmth that gets absorbed from the warm airstream into the cold airstream. Because there's a bit of leakage, and depending on the rotation of the wheel, of the speed of the rotation, those systems are not quite as efficient as heat recovery ventilation systems, but still high 80% efficiencies. The advantages of the system is that you don't need, for example, a condensate drain, because they're slightly less efficient, and the moisture that would condense from the cold air coming in, the warm air going out, and the cold metal, when the wheel rotates around, it actually gets rejected back to the outside. Other systems that are more efficient, that don't do that, where the cold air cools down the heat exchanger, the warm, moist air from the inside comes through, hits the cold heat exchanger, starts cooling, starts warming it up, but itself cooling down and creating condensation in this warm airstream. That condensation only can't go anywhere because the incoming airstream doesn't touch it, and you have to create a condensate drain. So if this is now in the middle of the building, for example, and you have a concrete slab, it's much, much harder, more difficult to actually then allow for that condensate drain to make sure you can actually drain this moisture that you generate in your heat exchanger towards the outside compared to this. So that's an advantage of the ERV versus the heat recovery ventilation. On the other hand, that one's a bit more efficient and it's got less moving parts. So you don't have to rotate the wheel. It's another thing that can break, or for example, there's another motor. And here you just have two fans, one pushing air in, the other one pushing air out. So a bit less maintenance required potentially. Then again, those motors are very robust. It's a very simple electric motors. Electric motors have been around now for many decades and work really well. So it's very low risk even for that to require maintenance. For ventilation to work really well, if you have a centralized system, you need to make sure that you design accordingly from the very beginning and make sure you have a proper ventilation layout. You can't just put a system in here and say, okay, I've got that many people, I need that much airflow, and then I just run a duct back here and one here to make sure every room gets some fresh air. This needs to be balanced properly. So good ventilation layout and design is very important. And again, that should be something that is considered from the very beginning. Pressure drops in the ducting should be considered, and sometimes some ducts need to be bigger than others. Some ducts might need to be restricted, and that's something that should be ideally kept in mind from the very beginning, because it has an impact on the building design itself. So to design for good ventilation, you have then to also allow for the ducting to run somewhere. Either that has to happen through lowered ceilings or bulkheads or other structures, because the really, really important thing is ducts must run on the inside of the thermal envelope. There's no point if I have cold air that was warmed up through the outgoing airstream is now on the inside ducting, being distributed through the rest of the building through ducting. If that ducting itself runs above your insulation and in your cold roof space, and all that warm air then cools down again. So it's really important that that ducting runs on the underside of the insulation on the inside, not on the outside. And again, in your design, in the building design, space needs to be created for that. And again, if that then is taken care of early in the design process of the building, it's easy to implement those kind of things, to take that into account and to allow for those duct runs to be inside. As I mentioned before, the ventilation layout needs to be balanced, otherwise it doesn't work. Some rooms might suffer, other rooms might get too much airflow. So make sure when you get a ventilation layout to ask for a layout showing the pressure drops to make sure it's properly balanced. The plant room itself also has to size accordingly. I've seen many plans, very nice building designs. People want to get a ventilation system because they want to build energy efficient, they want to build airtight, but there's no place to put it anywhere to get good access to it. The ventilation system still needs to at least access to change filters regularly if you want to keep the system working properly, and if you want to have clean air coming in. And again, as I mentioned before, you need to allow for condensate drain for HRV. So the placement of where the plant group might be is also dependent on your kind of design or construction. A slab, for example, it's much easier if you can use the ventilation system to the edge of a building rather than in the middle. That needs to be allowed for. For a decentralized system, it's a bit simpler. All you need to do is to allow for a bit of wall space to punch through for that individual unit. There's no ducting to be run. But again, for apartments, for example, it's very popular to have multi-residential structures that have just one glass front towards a balcony and no other external wall. If you design like that, then there's no space to put anywhere a ventilation system that can create fresh air. And in the end, the space doesn't really work as well as it could. So a bit of wall space has to be designed for. And keeping that in mind, I think from the very beginning, really, really helps with that. Now we've done all those great things. We've made our building airtight. We made it moisture tight. We made it wind tight, protected from the weather, and we allowed for ventilation. Unfortunately, this still doesn't give us 100% peace of mind with regards to condensation and mold, because there's one other factor. And that factor is what I mentioned at the beginning, gets often overlooked and disregarded because it's a bit more niche, a bit more difficult. Structural thermal breaks or structural thermal bridging itself is often put into the too hard basket. People know it exists. Everyone's seen thermal camera images, and yep, there's cold spots and there's connections where a concrete slab runs right through from the inside to the outside. But for builders and developers to get to a step where you can actually break the structure, of course, the structural integrity of the building is the most important thing. If the balcony falls off, that's the worst. Yep, thermal considerations are a bit of a secondary concern then. People are still unsure. It's a new technology relatively, and people don't know how to do it. So it's, as I said before, it's often put into the too hard baskets. What then happens in the end, we get condensation and mold, despite having a very well ventilated building, very airtight building, well protected building, because just we have surfaces on the inside that are so cold that they attract moisture, and you get condensation on those surfaces, just in those spots where those thermal bridges are. And very nice examples. They're very, very new buildings. This one is just a year old. You can see the banding on the steel structure of the purlins and rafters of the metal roof here. Mold growth behind the gyp rock slowly coming through already. So that's some significant moisture problem on the backside of the gyp rock, just because the cold steel, the cold metal touches the warm gyp rock here directly. Moisture getting through because it's diffusion open, and you get condensation. You get wet gyp rock, mold growth. The same here in a wall, in an apartment, yeah, very, very difficult after it happened to remediate. The only way really is to rip everything apart again, either get rid of the metal structure or create a significant distance from the inside surface to the structure with metals, with thermal breaks. Again, importance to design and consider those things from the very beginning. I don't think anyone wants to create those kind of living spaces, no matter how nicely architecturally they are designed. What exactly so is a structural thermal bridge? A structural component penetrating the thermal envelope. That's what the definition of a thermal bridge is. So that can be anything from a higher thermally conducting material than the surrounding insulation. And for example, that are often, as I said before, and showed in the pictures, balcony connections from the inside to the outside. Blade walls that just run straight through prefab and precast concrete, tilt-up concrete walls, and that don't have a thermal break. Parapets even, or steel beams, steel structures. Many construction designs with big spans, nice big glass, maybe shade structures on the outside require lightweight steel shading structures and tied back to the building structure, going straight through the building envelope, going straight through the insulation. And we all know steel is a very good conductor, so that would be a very big thermal bridge. Again, here, just summarizing all those problems, defining the problems to make it easier for us to find, to identify during the design phase. Cantilever balconies, for example, same with supported balconies. The base of walls, where walls sit on your footings that go directly down to the ground without any insulation or disconnect, because there's a structural connection. Parapets, as I mentioned before, just because they have such a large surface area and exposure to the outside, and often the parapet itself is not insulated because you think it's outside, it's external to the building. So it's a weak point in the structure. Or sandwich panels themselves. Concrete sandwich panels, again, you try to insulate, create a quick and easy to install structure, prefab, 2 concrete skins, but connected with a steel structural member going straight through. Very good thermal bridge. Again, here the red 10 test comes really handy during your design phase. You design your building, you run a red pen around the thermal envelope, and whenever you encounter one of those points where the structure penetrates your insulation, that's one point you have to address and to deal with. So you look for points where the insulation stops and where there's heavy and well-conducting structure. This can also be on the inside, just where floors connect to external walls, for example, not just where the whole structure runs straight through to the outside. So what types of thermal breaks exist? Again, the thermal bridges that I've covered before, pretty much for every thermal bridge that exists, there's also a thermal break that already has been developed. It's been around for a long time. The most used building material in the world is concrete. So concrete to concrete, and as I said before, thermal breaks would look like this, for example. In cantilevered balconies, for example, you have a load that stretches from the inside to the outside. You can't completely eliminate any kind of structural element going through, obviously, because, as I said before, the highest and most important point is the structural integrity of the building that comes before thermal considerations. But because that section is so small, normally what happens is just cheap steel reo runs straight through. We can now actually use a very small amount of high performance stainless steel that has the thermal conductivity only of about a quarter of the normal steel, and at the same time is stronger. So we can actually reduce the cross section of the steel that runs through the thermal bridge, and we can reduce the amount of steel that runs through as well. Yep, it's a lot more expensive, just this tiny little bit, but because it's such a small amount, just with the thermal bridges, not throughout the whole building, this is actually a worthwhile investment to make sure you don't run later down the track into condensation and mold issues and very expensive remediation. How do they work? There's a reason why those shear bars, again, are bent out to make installation very easy. As I said before, one of the biggest hurdles for adopting of thermal breaks is the fear of cost and difficulty of installation, and again, which comes essentially down to cost. They have been designed for many years to be very easily installed, and that's why this bar is bent up again. They can simply be dropped in a gap of the reinforcement work of the concrete on the inside to the concrete of the outside. Very fast installation, tied off to your normal reo, and concrete just simply poured over the top of the whole thing, and still not connecting inside and outside thermally. That's what it then looks like when it's installed. Ideally, the thermal break is installed with external building insulation in line, which is here the double glazing, for example, a bit of insulation and down to the next glass facade in a multi-residential environment, for example, with windows above and below the balcony. How well do they really work? As I said, thermal bridges can't be completely eliminated, but they can be significantly improved. And you can see here a untreated thermal bridge, simply the concrete running straight through. Sorry, this part, and on the right hand side, the structural thermal break installed, and the internal temperature where condensation could occur is significantly higher with a structural thermal break compared to the outside. So it reduces the risk of condensation because you reduce the amount of cold spots that are created by thermal bridges. Then there's other types of structural thermal breaks, as I said. So there's concrete, of course, there's also steel structures. Steel is very highly conductive, but it's also a very efficient structural member. So it's a bit more difficult to thermally break than concrete and to achieve the same performance. There's two main kinds of structural thermal break again. The first that was kind of developed is a simple kind of very high compression plate, but with a lower thermal conductivity than the steel itself to separate the internal from the outside steel member. Problem here is that the thermal break has to be very small to support shear loads. So the bigger this plate is to create a good structural thermal break, the longer the bolts have to be. And because this plate itself is a weaker structural member, in the end, the whole shear load is held by the longer and longer bolts, making that connection weaker. And there's a limit how far you can go. Either you have to increase the number of bolts significantly to still hold the load, and in the end, you end up with a amount of steel going through the juncture just through the bolts that's actually greater than you would be by running the steel straight through, or you have to make the thermal break quite small, and then it's not that good. There's another type of thermal break though as well, where rather than just having a compressive plate, you always keep the loads very close to the end flanges of the steel. And that's done by, rather than having a long connection unsupported through the middle, there's a flange plate directly touching the steel on the other side. There's a very, very strong, again, high performance, more expensive, but not much of a high performance steel. Sorry, too far a bit here. And the load is basically connected directly from the flange through this section onto the other flange, and creating a very, very strong connection with a much bigger distance. Because this connection is so much stronger than that plate, you can again use less for bigger loads and create a better outcome for steel-to-steel thermal break. And again, here you can see the differences between the two in terms of performance. The thin 10 millimeter solid plate going all the way through, 0 degrees conditions outside, 20 inside, but right in the corner, closest to the outside where it conducts some heat flow through, it still gets fairly cold down to potentially into areas where you can get some condensation involved. With this greater distance and lesser contact area between inside and outside, you get much better performance. Then there's other hybrid types. Of course, we have hybrid construction. There might be a concrete building that has some steel attached to it, like steel shading structures or balconies or awnings, where you can have a steel to concrete thermal break that gets concreted in first, and later you have those bolts sticking out that you can attach your steel structure to. Or again, for sandwich panels, you have options now, or rain screen facades, where you have a concrete panel that can be precast with a thermal distance piece, can be over insulated, and then in the end there's a screw connector that your rain screen facade or potentially external concrete skin also could be poured onto and connect inside from outside face structurally, but without any thermal connection at all. So this structural part here is actually fiberglass structural member that's thermally virtually non-conducting compared to steel directly. There's also structural thermal disconnect blocks for masonry construction, for example. Here used, for example, on the right-hand side, in a cold concrete slab that has insulation layer on top of it and a warm screed on top of it again. But then there would be normally a masonry wall sitting on the cold slab because it has to be a structural connection. This thermal block can continue the insulation through the masonry wall without gap and still structurally carry the whole load of the wall. There's again a high performance aerated concrete that has a much lower thermal conductivity, but still reasonably high strength to carry those loads, but lower thermal conductivity compared to normal concrete, compared to the rest of the blockwork wall. As I said before, structural thermal breaks are still a bit of a niche product and often fall victim to value engineering because people are scared away from difficulties of insulation and then increased and connected costs with that. There's a very famous example, beautiful architecture. Architects, I guess, know this building, the Aqua Tower in Chicago. When it was designed, it had very high ambitions also for sustainability, and it was actually designed with structural thermal breaks in mind. When it then came towards value engineering and developer coming together with a builder, trying to figure out costs for this building, everyone scared away, and they thought, okay, we need to try to achieve a high thermal performance. Structural thermal breaks we don't really know how they work. They're fairly new. Let's maybe not worry about them, and let's instead just increase some other factor, increase the insulation in the wall, so use better glazing that we know how it works, and get overall the same thermal performance of the building. So in the end, the building got certified, but what happened was massive thermal breaching on those balconies. And not only have we heat leakage just through those direct connections from the inside to the outside, but everyone also knows that Chicago is called the city of winds, a very windy place that even increases then the heat transfer from the inside to the outside by cooling down those balconies that almost look like a fin on a heat exchanger. So you can really easily compare it to like the cooling fins on a motorcycle engine, for example, that's cooled just by wind going past. And the same thing here happening on the waterfall tower, the water tower, causing those balconies to cool down disproportionately more than they normally would with those high winds, and creating a very, very strong thermal bridge. And the end result of not having thermal breaks installed is massive condensation issues, a class action against the developer and builder, and sometimes jokingly called as the waterfall tower instead of the aqua tower, the greatest indoor waterfall in the world, just because there's so much moisture generated on the inside surfaces and condensation problems. Could have easily been avoided if they would have stuck to their guns and stuck with thermal bridging, thermal disconnects. And again, as I said before, not using an imbalanced approach, but making sure that all the aspects of the building are considered equally. Okay, so again, summarizing this presentation with this slide, again, also showing the importance, how important it is to not only consider every aspect of the building from the design stage, but then also to stick to it using a balanced approach during design and during construction. Stick to your guns, pull it all the way through, create healthy buildings and comfortable buildings, and make your clients and yourself happy. Thanks very much for your attention. Thanks very much for your attention. And I'll go over to the question part of this presentation now. Thanks.